Hello and welcome to this RFIC Inductor Toolkit tutorial. My name is Volker Muehlhaus and today we will look at technology customization for Inductor Toolkit Generic. Generic means that version which can be configured by the end user for different RFIC technologies. Other versions of Inductor Toolkit are fixed for just one technology and cannot be configured by the end user, but Generic offers additional files, additional functionality so that it can be used for different technologies after you, the user, have configured it. And today we will see how this configuration is done. And we will configure Inductor Toolkit to use technology from an existing PDK, from an existing ADS PDK, which already has layers defined and also has an existing momentum substrate file. For those cases where this is not available and you need to really start from scratch, we provide a little tool, a material that can read Assura proc files and export as an ADS substrate file. Okay, let's get started. So we have a directory which has our something PDK that we want to use later, and we have the Inductor Toolkit Generic, which is factory pre-configured for GPDK but can be customized. Just to be better organized and see what we are doing, it makes sense to create a copy of this and change the name to reflect the technology. So this will be our Inductor Toolkit something. If we want to see this in the list of ADS PDKs as Inductor Toolkit something, there is one extra change needed. So we need to go in here, go to the Inductor Shapes library, go to esoflib.config, where the design kit name is defined, and design kit name Inductor Toolkit something. Okay. So we need to have these design kits in our design kit favorites in ADS to make our life a little bit easier. So add library definition file. We have the something PDK in our list of PDKs, and we want to have our Inductor Toolkit something in the list of PDKs. Something PDK and Inductor Toolkit something, which we renamed because otherwise it would be Inductor Toolkit Generic. Okay, we now create a new workspace, and in this workspace we include the something PDK and we include the Inductor Toolkit something. And for technology for this workspace we use the something PDK. So later we work on the something PDK. IC interoperability is set to be compatible with other IC tools, so we use this with Cadence RFIC workflow compatibility. Okay, so this loads, and if you load this for the first time, you might see a PDF pop up which wants you to agree to the license conditions of Inductor Toolkit. And now we are ready to go. To do the customization, we have two basic steps. One step is to set up a text configuration file in Inductor Toolkit to tell Inductor Toolkit what layers to draw on and what dimensions, etc. And the other part is the customization or the mapping of Inductor Toolkit in ADS to use the correct technology. And that's what we are going to do first. So we go to Options, Technologies, Technology Setup, and go to Inductor EM Models lib. And this at the moment is pre-configured with the Inductor Toolkit factory configured layers, and we changed that. We removed the reference library and instead we use the something PDK library. And that's it. ADS tells us this will change the database unit possibly. We understand that. Okay, it's updating. And just to make sure everything is loaded properly, we just reload the workspace. And now if we go to one of the EM models and check, we see that everything's gray. And that's because Inductor Toolkit does draw on the wrong layers now. So Inductor Toolkit does not know that it now should draw on these something technology layer numbers. So we need to fix this. We go to the Inductor Toolkit something directory, and there is a directory called configuration. In configuration, we go to technology.ael, and this is where Inductor Toolkit wants us to configure the layers to draw on. Our something technology just has 4 metal layers, 3 via layers, so we can simplify this a little bit. And basically, this is AEL scripting, the ADS scripting language, and to make things a little bit more readable, we have a text declaration to the layer mapping first, and then later with the functional mappings, we use the text name. So our something technology has 3 via layers, 4 metal layers. The metal layer names are metal 1 to 4. The metal layer numbers are 1, 2, 3, 4. And the vias are 5, 6, and 7. So this is to declare that the ADS layer number 4, we call this metal 4. And here now we assign the functional layers, so the spiral layers where Inductor Toolkit draws the main circular spiral. That's on metal 4, which is the uppermost layer in this technology. The crossover is on metal 3. The underpass is on metal 2. A possible second underpass is on metal 1. The via layer, the main via layer between the spiral and the underpass, that's on via 3, via 2, and via 1. And for pattern ground shield, we don't have an extra layer, so we can use metal 1 here, or we can just set this to layer number 0. So this is mapping Inductor Toolkit functional layers, spiral, crossover, underpass to layer numbers in the ADS technology that we are using. Very, very simple and straightforward. The next setting is the minimum and maximum line widths. This is a check in the input dialog where we can figure the geometry range for our inductor synthesis to check this against technology rules. So the minimum line width and the minimum spacing in our something technology is 2 micron, and the maximum line width is 20 micron. Here, this is for the underpass, also dimension rules. So the maximum underpass width on that layer, it's 20 micron, and the underpass width factor. The underpass is on a lower layer, which typically has less metal thickness, so we make it a little bit wider. And this is a factor 2 that tells Inductor Toolkit to make the underpass twice as wide as the spiral layer itself, but no wider than 20 micron, which is a technology limitation. Okay, the next section tells Inductor Toolkit how to draw the via arrays. You could take it out and just say define via arrays false, which then means that vias are just drawn as one bounding rectangle. Typically, we want to draw the complete via array, and in this case, we have for every via layer We have for every via layer 3 settings. One setting is the size of the single via. In this case, it's 0.2 micron for the via. It can be different on the different layers, so we have via 1, 2, via 3 could be different values. The next setting is the distance between two single vias in the via array. Again, you get this from the process description, layout rules, for example. And the third setting is the distance from a single via edge to the surrounding metal edge. So how far the vias must be from the bounding metal on the layer above and below. We just leave these settings here. It really depends on your design rule manual what values you need to use. And as said, if you don't want to go into this detail, you can take all this out or leave it by default and just set define via array to false, then you just get one bounding rectangle. For EM simulation, we do have via merging anyway, so for EM itself, we will always use a merged via array, not the individual vias. Technology, last section, extra layers, dimension of extra layer boundary. In some technologies, we have layers like an inductor marking layer, keep out layers, no filler areas, etc., etc. And here's a list where you can put in, separated by comma, extra layers which are drawn around below and around the inductor with a certain margin, which might be required by your PDK design rule check. You can just take this out. If you don't want to have extra layers drawn, just make an empty list. That's fine. Okay. Store the technology.ael, go to ADS and reload your workspace so that the new settings are effective. Now if we open one of the EM models, we see that something is drawn here, so the layer mapping is effective. So we now have the main spiral on this white layer. This white layer is metal 4. It's the uppermost layer. That's what we wanted. We see the crossover. We see the vias. But the pins, the EM pins, are still on the wrong layers. And if there is a different database unit used in this technology, we might see the pins in the wrong layers. So we need to fix the pins. That's simple because it's automated. Go to Settings, Update, EM Model, Pin Layer and Position from technology.ael. Okay. So you see a message. EM model layouts updated, pin positions updated, pins moved to layer metal 4 drawing. That's where we have the pins. You see now the pins are on the correct layer, and that's true for all these EM models. Okay, if we look at one of these EM setups, we will see that the substrate is still pointing to the wrong substrate, and that's something we need to fix. Choose momentum substrate file, and we want to use the substrate from the something PDK instead of the factory shipped GPDK. So something PDK Okay, and now if we check, we see that now all these EM models in the inductor EM model lib, now they use the something PDK substrate. That's it. And now we are ready. Are we ready? Yeah, there's one final little detail. The menu still says Inductor Toolkit GPDK. So we might want to go to our technology.ael and change the menu name. So we call this Inductor Toolkit something. Save technology.ael, reload the workspace, Inductor Toolkit something. And that's it. So we can now give it a try. Differential octagon inductor, set target value, and you see DRC warning. Technology limit for maximum width is 20 micron, and pre-configured in this dialog was 30. So yes, the warning works. DRC mini super trivial DRC works, and the warning goes away when we set the geometry search range from 5 to 20. Just to see that this really works, we start the parameter sweep. And this takes a little bit longer now because the substrate calculation must be done first. So this is just a one-time thing to calculate the substrate for our something technology. Okay, this looks good because it just looks like the typical curves. We have inductance, we have Q factor, we have series resistance, and our target frequency is, for example, 12 gigahertz. Okay, this is the best inductor at 12 gigahertz. Do the fine-tune step. For this case, the octa, there's an EM setup defined here, this fine-tune EM octa, which has a little bit a better, more accurate EM setting. So that's why this took just a second longer. Okay, so here's our final inductor. 1 nanohenry we wanted, 0.99 we get, so all that looks great. And now we need to find the ADS window, create inductor cell in library. And so in my library, we have the cell octagon differential 1 nanohenry. Okay, this is a single turn, so we haven't restricted the size very much, so the single turn gives the best Q factor here. In the very beginning, I forgot to restrict the size, the maximum area, so we get the single turn. But anyway, we see it all lands on the right layers, so this all works, and we have successfully configured our inductor toolkit for the something technology. To reuse it, you might want to copy this directory, zip it away for reuse, just to avoid that you by mistake changed something on the technology if you want to share it with colleagues. That's it. Thank you very much. And just if you are interested in the creating technology from scratch using the material tool that reads Assura proc files and exports as an ADS substrate, I will do a new video on that topic in the coming weeks. Thanks and bye-bye.